Hello and welcome to Lesson 12-4, Part 2. We're going to continue with our discussion of limits. We're almost to the end of the year as we know it here. Only 2 more lessons after this. We're talking today about limits of sequences. Limits of sequences have many of the same properties as limits of functions. For example, consider the sequence whose nth term is a sub n equals 1 over 2 to the nth power. As you can see, it would go then 1/2, next one would be 1/4, then 1/8, then 1/16, 1/32. As increases without bound, the terms of the sequence get closer and closer to 0. Therefore, the sequence is said to converge to 0. Using limit notation, you could write it as the limit as n approaches infinity of 1 over 2 to the nth power equals 0. Think of this also as when we had an infinite sum of a series in the last chapter. Same concept. The following relationship shows how the limits of functions of x can be used to evaluate the limit of a sequence. So let f be a function of a real variable such that the limit as x approaches infinity of f of x equals L. So if a sub n is a sequence such that f of n equals a sub n for every positive integer n, then the limit as n approaches infinity of a sub n equals L. A sequence that does not diverge or does not converge is said to diverge. For example, the terms of a sequence 1, -1, 1, -1, 1, so on and so forth, they oscillate between 1 and -1. Therefore, the sequence diverges because it does not approach a unique number. In this first example, evaluating the limit of a sequence, we're going to find the limit of each of these sequences as they approach infinity, assuming that n begins with 1. Well, in each of these cases, we can begin to see a pattern arise. So, for example, the limit as n approaches infinity of 2n plus 1 over n plus 4 equals 2. As we write out the terms of the sequence, we see that it's getting closer and closer and closer to 2. We could graph this sequence or graph this function and see that it's getting closer and closer and closer to 2 as n approaches infinity. We also notice that the 2 first terms, being 2n over n, reduce to 2, which is kind of neat. Notice in the second one that you have a 2n over n squared. Well, as they reduce, they approach 0. Why? Because you have a 1 over n squared in the bottom, and so if you were to reduce that, you get basically 0. The limit of, as n approaches infinity, of 2n squared plus 1 over 4n squared would be 1/2. You know, we would want to approach these the same way we did in the last half of this lesson, that being the limit as x approaches infinity of 1 over x squared. And remember how in each part of the fraction we divided it by x squared, and then for every 1 over x squared or x to any power that we had, we put that as 0. We're going to do the exact same thing here. Okay, in the first one, you would just simply have 2 plus 0 over 1 plus 0, which is 2. In the second one, you would get 2n over n squared, which would be 1 over n, which is 0, plus 1 over n squared, which is 0. So 0 plus 0 over 1 plus 0, which is 0. And in the second one, you would just get 2 plus 0 over 4, thus being 2 over 4, which is 1/2. In this example, find the limit of the sequence whose nth term is the following equation. We can begin by writing the nth term in a standard rational function form as the ratio of 2 polynomials. When I divide, or when I multiply all this through, I'm going to basically refoil all of this. I've got 8 times n plus 1 times 2n plus 1 and n cubed times 6. I'm going to basically combine them all out to write it in a standard rational form. Now, once I get that, from this form we can see that the degree of the numerator is equal to the degree of the denominator. So as a result, the limit of the sequence is the ratio of the coefficients, which is 8 over 3. On the right, we show you a numerical version of doing this. The first term is 8. The 10th term, 3.08. 100th term, 2.707. 1,000th term, 2.671. The 10,000th term, 2.667. As you can see from this one, as n approaches infinity, this is getting closer and closer and closer and closer to 2.667, which is in fact 8 over 3. Now, what you could do, though, over here is you could basically take your rule of where we divide everything by the highest variable with power in the denominator and just divide it through. So you would get 8 plus 12 over n plus 4 over n squared over 3, which would basically just get you 8 plus 0 over 3, which is 8 over 3.